Thank you for the invitation. So motivation for this talk will be the following. So there is expected to be a one-to-one correspondence between so Fano varieties, and let me put with mild singularities, and Laurent polynomials.
Yeah, right.
You were not paying attention. Everything was in.
You're right, I didn't pay attention.
Smoothing. I think this will be
Plurality or singularities?
yeah, okay, singularities. I will mostly speak about affine ones, so. But also variety. Okay. Okay, so Laurent polynomials, and I'll just put with with nice properties. And I will define what these nice properties are later. And in fact, this correspondence, you can also look this up to Gorenstein deformations, and this set up to mutations. And so originally, like the first approach, was so the statement was formulated by so Galkin, Coates, Corti, Kastridge, Golisha. And so in so what was expected, so so this is kind of a mirror symmetry statement. And so it was expected to so the idea was to classify Fano varieties using this mirror symmetry. And more precisely, so from Laurent polynomial f, it is expected to get Fano variety, so a corresponding Fano variety by deforming. So now Fano toric, singular Fano toric. So singular Fano toric variety given by the Newton polytope of F. So you take a spanning fan, and that's kind of the first approach to this correspondence. So okay, with nice properties, in particular, Newton polytope should be Fano, so only one interior lattice point, and then you take a spanning fan. This is your singular Fano toric variety, and it is expected to, like, if you deform it, in the general fiber should be like you deform it with this Laurent polynomial. I will talk later about some technical parts of this, but yeah, then it should be expected to get a Fano variety. Okay, and then like in this, so I will also mention a second approach, which is more recent. Yeah, sure.
Surely, so toric is corresponding to the Newton diagram is the so
in the this is I mean, okay, this is n-word. You take polytope which has only one interior lattice point, you take a spanning fan, and this is your singular toric.
Usually then it's consider Laurent polynomials, and the Newton diagram of that is not in the affine, it's in the poles.
So I didn't. So I mean, like depending on which strategy you use. So of course you need to say how. So you say how you will deform with F. But so far this is just in N, and you take a spanning fan, and then F helps you deforming it. So that's the idea. More questions? And okay, a second approach is using log structures. So by generalizing work of Gross-Siebert, so let me here mention our work with Helge and Simon. So smoothing toroidal crossing spaces. So Helge will talk about even generalizing this. So the idea is from F to build a log structure, and then with this log structure you are able to smooth or deform varieties that locally look like a boundary of a Gorenstein toric variety. So but this will be like Helge's logs. Okay, so today I will talk about like a special part of this one-to-one correspondence that was introduced to me by Alessio Corti, and so the conjecture is conjecture by so Alessio Corti, myself, and Petracci. Andrea Petracci, is that now I will talk about singularities. So X should be affine toric variety. In fact, if we just do toric deformation theory, this affine thing is not very restrictive, because if you understand all the affine deformations, then by comparison theorem, you understand also projective ones. So, so if you have affine toric variety, okay, toric affine Gorenstein toric threefold, then the statement is that there is a one-to-one between so smoothing universal deformation components of X and something called zero mutable Laurent polynomial. And I will introduce what is known about deformation. I will say what is known about deformation theory of toric varieties so far, and also I will explain what this zero mutable means. Okay, so first, this side, so what is known about deformation theory of toric varieties. So there is a, in two dimensions, so like this X, let me just say X affine. So two-dimensional case is known by, so the universal deformation is very well known by the work of Collar and Shepard-Barron from the 90s. So universal deformation, well known And then there is, in the case of isolated Gorenstein toric singularities, so affine isolated Gorenstein, there is a work again in the 90s by Klaus Hartmann. So the universal deformation constructed by Altman. And moreover, and the reduced, irreducible components are in one-to-one correspondence with Minkowski sums of polytope that is defining Gorenstein toric variety. So I mean Gorenstein maybe my setting will always be that sigma will be cone. I will talk about Gorenstein toric varieties from now on. So I will take a polytope P. Sigma will be like you put polytope on the height 1 level, you build a cone over this, and this would be in n tilde, which is n direct sum with that, and then spec of sigma dual is our affine Gorenstein toric variety. So when I talk about P, I mean this P. And so being isolated means that P has edges of lattice length 1. So this is a restriction on P. And the conjecture here is that, I mean, like, the important thing is to not isolate it. So to have a general, so try to understand the universal deformation space for non-isolated Gorenstein toric varieties. So what I mean by this correspondence one-to-one, so for example, if I take hexagon, so all the lattice edges have all the edges have lattice length 1, and I take this. So I know I should take like this and then this. So sum means just Minkowski sum. So when you add, you will just get this hexagon, and this plus this plus this. So the statement is that you just take all these Minkowski summons, and this tells you that you have two universal deformation components, and in fact, the dimension is how many summons you have minus 1. So this is one parameter family. This is 2 parameter family. So the universal deformation in the isolated case is completely understood. Yeah. Questions so far?
When you say reduced irreducible components.
Yes.
So if there's a non-reduced irreducible component, is it not in a correspondence? Is the space reduced?
No, I mean the universal deformation is not reduced. So then I mean what's happening with the non-reduced ones? I don't know. But I mean okay, so you have so what is known is that the universal deformation is completely described and it's not reduced. And then if you take the reduced and you look at the irreducible components, those are the ones. So and the other thing.
So you don't take the reduction of the space and then the components, but you do say a primary decomposition, and then you look only at the reduced components.
so what's the like? Okay, so it's looked by okay reduction. You look at the reduced guy, and then you look at the components of this guy.
So when the base of the universal family is x times y squared is 0, then there are two components, or one.
Again, x times y squared.
So one or two components in this correspondence.
Okay. So two components then.
Two.
More questions? Okay. Then. Okay, let me introduce this side of the. Maybe before. So both of these results are known from the 90s, and this and this one. So it's a long time ago. And before I introduce what zero mutable actually means, so lately there are some results about deformation theory of toric varieties by so Altman, Constantinescu, and myself. So we have two papers, but basically what we did was we just take some of the we just take the tangent space of this deformation is it's I mean the lattice induces the grading on the tangent space. So and we just look at the special degrees of this deformation. So we were not able to understand the whole deformation. Speaking about knowing the whole universal deformation, these are basically the only two results that exist. Okay, and now, so this is this side, what was known, and today I will talk more about non-isolated Gorenstein, so about this conjecture. And then on this side, we have, so let me now say what actually zero mutable means, and first, what a mutation is. So, so F Laurent polynomial is, and I will use mg mutable. So, okay, for the purpose of this talk, F will be inside Cn, and so this is like Z square, so two variables, x and y. I will present Laurent polynomials because we are doing threefold, so putting polygon on the height one. Mg mutable, so this m is affine function on P, and why I denote it by m, because we look at the we look m as an element of m tilde. And then m tilde defines an affine function on height one. That's why I use this notation. And this g is just Laurent polynomial. So is mg mutable if we can write f as a sum of fi, where fi is, I will give an example. So lies in this hyperplane defined by where this affine function is equal to I. Such that fi divided by g on I is Laurent polynomial. So this is also known as a combinatorial mutation. And then we just say that the mutation by this pair, so G and M of F, is sum of these guys. Let me give an example. So example is take if we take 1, 2, 1, 3, 3, 1, and here I take 2. So this is a Laurent polynomial 1 plus 3x plus 3x squared plus x 1, 3, and then plus 2y plus 2xy plus y squared. And so if I take affine function m to be so here to be to has value 3, here value 1, and here value minus 1. So this is an affine function on this example, and I take g to be 1 plus x. Then we see that this notation means that this is f3, this is f1, and this is f minus 1. And the condition is that f3 is divisible by 1 plus x on 3, which it is, and that this guy is divisible by 1 plus x. Okay? And the mutation is then equal to the following guy. 1, 2, 1, 1. Because we divide this by 3, we just get 1. We divide this by 1, so we get like 1 less, and then this one we multiply by 1 plus x, and if you do this, you just get this guy. Make sense? Any questions? Like, I'm not sure. I mean, if you've seen a combinatorial mutation, then of course it's clear. Okay. Now what means zero mutable? So f is zero mutable if we can mutate it to a point. So clearly here we can take another affine function to be 2 here, 0 here, and we take 1 plus y to be a Laurent polynomial, and we will just get an h, and then we can also mutate this h to the points, and this is called zero mutable. And basically, if we fix polytope, then it's not so hard to get those zero mutables, because basically zero mutables, this is a proposition in our paper with Petracci and Forti. That zero mutables are the same as rigid maximally mutable Laurent polynomials, and this just means that okay, on the edges we put binomial coefficients, and then every other lattice point needs to be the coefficient needs to actually come from one of the coefficients on the edges. So basically, we can take here 2, 1, 0, minus 1, and then because this is divisible by 1, this needs to be 3. And the other option is this one. So like either you take 2, 1, 0 or 3, 1, minus 1. So it means that this coefficient is, to say that this is mutable, then this coefficient is fixed and it needs to be 2, because otherwise this is not divisible by 1 plus x. So these are the only 2 zero mutables in this case. And in fact, this corresponds to the, this example has 2 smoothing deformation components corresponding to this and this guy. And now another conjecture that we have, and this is more so to actually construct it, so to actually make the first conjecture more explicit, so the miniversal, the smoothing component coming from F is a deformation of our affine toric threefold over over this guy, and F is mg mutable. And I will. So this is those are the parameters corresponding to the one parameter deformation given by mg, and this is I'll just state in a remark. So given a mutation mg of f. So if f is mg mutable, then there exists a one parameter deformation of x, which is, okay, geometrically, we can see this, so geometrically, we can see that this is one parameter deformation because if we take sigma, so our cone, intersected by hyperplane where this m equals 1, has a Minkowski summand delta G. And by the deformation theory developed by Klaus Altmann, then we know that actually this is, there exists a one parameter deformation. So basically mutations are the same as, if I give mutation, it's the same as I give one parameter deformation. And then this conjecture says that we can actually explicitly compute, that
one was for isolated singularities, so there is.
Yeah. So okay, the whole universal deformation is known for isolated Gorenstein, but this statement that so if you have any so for example, if you take any polyhedra that you can find the lattice polytope as a summand, then this actually induces one parameter deformation. This is clear. So, but of course, it doesn't mean that we understand the deformation space of this guy. So basically, if you can decompose with Minkowski summands any kind of, not necessarily just Gorenstein, then this induces the corresponding R parameter deformation. This is known in general, but this is not the miniversal deformation. This is just some deformation. So in particular, in this case, you have this as a summand. If we look at this example, so you take a cone and then you picture this m, so the hyperplane m equals 1, which means like the Newton polytope of G will be this guy. And you really see that this is a summand of this divided by n equal 1. Because this will be an, I mean, when you divide this by 3, it will have one edge. And so, okay, this one, it will still be there, and then there is no condition there. So you will have this as a Minkowski summand. And then by the known deformation theory, in principle, you know that there exists a one-parameter deformation. And this is what more or less we know. And then the statement was, okay, we believe that now given Laurent polynomial, this is the component. So basically explicitly stating that those one-parameter deformation we know that exist, and they are unobstructed. So Laurent polynomial basically tells us which one-parameter deformations are unobstructed and lead to the whole r-parameter deformation family. Okay. So for example here, okay, maybe I need to mention that the tangent space in the non-isolated case is infinite dimensional. But in the so if we are in the affine 3 case, then if we look at the Maurer-Cartan equations of the Harrison-DGLA, then we expect to have, I mean, not expect, then we know that there are only finitely many equations. So, so the deformation theory in this case works as the usual when the tangent space is finite. But in general, this is infinite dimensional, and so these guys are, in particular, this is infinitely many variables. So, for example, in this case, if we take this, then we know that 3, 1, minus 1, this is 1 degree that we have here, and then also 2, 1, 0, and so on, and infinitely many. So also like 4, 1, minus 2, and so on. All those are deformation parameters. But what is important is that you cannot take, for example, 2, 1, 0, and 2, 1, 0. This is actually an equation, so x times y, if you take the corresponding, because there is no Laurent polynomials that will be mutable by 2, 1, 0 and 2, 1, 0, because this is then a problem. So this is the idea behind. Laurent polynomial tells you which one parameter deformations are unobstructed. That's the so in the rest of this talk I will say more about the proof and why we expect this to be smoothing. Is the statement clear? Okay. Okay, so I was working on this conjecture now for a while.
So it says that this one components are smooth. You can say the relation. What I understand.
So I'm just saying that so this conjecture is basically that so there are two important statements. First is that those one parameter deformations are unobstructed, and that they actually build a component in the universal deformation. This is the statement saying. So these two things you need to understand. Okay. No questions? Okay, and so now even it, I mean, so I mean, the idea behind this conjecture is that because they were known by results of Nathan Hilton that okay, in some setting that if you have a if you take a mutation that you have a deformation family over P1. So but this is in a projective setting. So basically, the idea is that somehow this and this guy are related via some deformation over P1, and so this is like the fiber over 0, and then this is the fiber over infinity in some sense. So the idea was that okay, if we mutate to something smooth, then this and if they have the same deformation components, then we should expect the smoothing. But so I would.
Do you have the conjecture of how these components meet?
So yes, precisely at those parameters that have in common, they intersect. So it's actually expected that that those components will be over. So it will be as in the Altman case, which is also our parameter. Here also, like it should be like there is no like. So it's actually infinitely. It will be affine spaces, but infinite dimension. Those will be, and I mean here. The tangent space, it's basically, okay, G here is, in the three-dimensional case, is basically irrelevant, because for G I always take like 1 plus x, so it means like I'm taking the Laurent polynomial that have, that his Newton polytope has a lattice length 1, and it's parallel to the given affine function. So basically just the affine function, just this element m is important. And then those are the coordinates, and yeah, you immediately see if they have the same. If they have the same m, then those intersection. I mean those components intersect in those affine spaces. Okay. Okay, now a few like notation. So so the original idea was that it should be somehow proved geometrically, but then it turns out that like we have no idea. It's also yeah. So then I just started doing the same thing as Klaus Altmann did in the 90s. So basically, trying to construct universal deformation using the computational flatness criterion. So, like the first major statement is that this is actually unobstructed. So basically, I was trying to construct the deformation over this guy, and even though it looks that maybe would be much easier to do it geometrically, we have no idea how to do it. So I just I will present how to do it via algebra. So, and of course then the proofs are more messy. So because we need to introduce some. So I will introduce some notation and then give an idea of the proof. So notation will be, I will, so the ideal of x will be is generated by fk, where k is in nr, and this fk is, I will just denote it by x, and I will introduce those. I will say what these guys are, just on a concrete example coming from this one. So first we fix a basis of sigma dual intersected by m. So in this case we have this guy. It doesn't need to be the minimal basis or the Hilbert basis, but just any basis. So we have, let's say that we take a Hilbert basis. So we have this guy, and this guy. So if I put this to be our vertex 0, then I have here value 0, 0, 2, 4, 3, 6. So the elements are 1, 0, 0, 0, 1, 0, and so on. So we all know how to construct the this guy, and and then what I'm using in this notation is that I will use the following. So I will denote the following. So I will denote by S1, S2, S3, S4, S5, S6, and this will be U because this is the Gorenstein degree 0, 0, 1. So this guy is 1. And so when I say this notation, what I actually mean is that so our ideal lies inside x1 to xr and u. And these x are so the variables corresponding to those s's. And then we have additional u, which is the Gorenstein degree. Okay, here I usually denote by r star. So this is r star is always the Gorenstein degree, all zeros, and then then 1. Okay, so this is how where the ideal sits, and then so those fk's are, so if I take, let's say, f, and then I take 0, 1, 0, 0, 0, 1, this means I'm taking x2 because this is 1, and then I'm taking x6. So this is this guy. This is x to the k. So I'm just like, this is element of nr, and I'm just taking the powers. And then, so this guy means that if we sum this guy, then there is a unique decomposition of boundary element and the Gorenstein degree. And this I'm taking here. So, for example, if I'm doing this guy, we see that 0 plus 3 is 3, so I get x5 and u. Or to write it in this way, u times x5. So this means this notation. And okay, so why I'm saying this is because there is a nice so I introduce this notation because there is a nice proposition. For example, this proposition Klaus Hartmann didn't have in proving, which would be a lot more helpful in the 90s. So proposition is that the module of linear relations between fk is generated by the following relation. So, which is fa plus k minus say fk. So the point is, we just have one relation, okay, for all a, k, and r. And the idea is we just need to lift fk and lift only this relation, and then we can use the equation of flatness criterion. So, and to prove flatness, this is, and this is proposition in one of our papers by, so I'll come. Okay, questions? And so
What you said that too? Are you proving that conjecture?
I'm so first, yeah, I will, yeah, this is the conjecture.
So this is the main result of this talk.
So the main result of my talk is that I can at least prove this conjecture for x. So with some restriction on the polytope, in particular for all the facets of the reflexive three-dimensional polytopes will work. So the result that I will present is that this holds over this time. That's what I will do now. And also I will explain how to, I will even slightly generalize this conjecture and to say also what are conjecturally singular components. That's the idea. Okay, so having this, then so then I was able to there exists lifting this relation. So lifting this, and I will just say in some cases, there are some there's some technical condition that I don't wanna introduce now. But what I wanted to say is that so how in fact like the idea how to construct it and why we expect to get a smoothing from this. And the idea is the following. So this fk will.
One dimensional more or so one more dimension, just a smoothing. One more dimension, one more.
No, in all the so in fact okay. So the first the first breakthrough was to actually construct one parameter deformations, the one that I mentioned here, but now explicitly. This was not known, and this is actually a very nice formula, but I don't have time to actually give it. So first, what I did was to construct this one parameter deformation explicitly. So in this fk, but then also like the main thing is to extend this one parameter deformation to the whole thing. And then there are some conditions, but yeah, so in particular here I'm using more than one parameter deformation. So I like infinitely many parameters I'm using and lifting only this relation. But I mean, this is actually important because Altman didn't have this in 19, so he actually needs to deal with more relations, and then it's very hard to guess the lift. So this is actually then here it's still hard, but more accessible. Okay, so the way this works is I will just give an example here, and then hopefully it will make sense. So if I take this guy here, so I'm taking this guy and this guy. So basically this corresponds to f. So in this notation means 0, 1 because I'm taking the second one, and then there is 0, 0, 1, 0. So this guy is x 2 times x yes, times x5. And then, okay, this is minus ux4. And the way the lifting works, so now I will just take two parameters. So the t parameter will have degree we'll have the following degree. So minus 1, 0, 1. So the t will look like element here with 1. So if you look at the corresponding polytope, this will be the affine function 1, 0, minus 1, and so on. So this is parameter t. I'm not using anymore the subscript mg because it's only relevant the degree. And then s will have parameter 0, minus 2, minus 2 and 3. So this is the guy that we have at the beginning. So so s corresponds to, this is our s. So 3, 1, minus 1, and then t is here, which is 1, 0, 1, 0, minus 1. Okay, and the point is that I have some technical formula for this guy, which in this case looks like this. So is just minus ts, and if you look at the degrees, so this is like 1, and this is 3, and this together is 5. So I still need u here to make it. So t times s times u. This is how it looks. This guy. I mean, this is of course proposition, but what I wanted to like the main point of how the conjecture will be proved in general, or I mean at least how I managed to prove it in those cases that I mentioned, is that now that when you mutate, so we were mutating this guy to this thing, And in fact, you also mutate this guy here. So everything mutates. So all the Hilbert basis element mutates up. So this guy goes here, this guy goes here, this guy goes here. And the nice thing is that also by a formula, which, as I said, it's some technical notation, so I'm not mentioning, also this guy mutates. So how it mutates is just it's just using. So I'll just if I write this to represent this guy, then in the mutation picture, this guy is up here and up here. So mutation will leave this guy here, and this one stays there. And then so this is another. In this affine toric variety, this f is actually so you multiply this guy by s minus 1 to something, and it turns out to be so that the lift is okay. Now I'm using the same variables, just until down. So this is the same, and then because I'm using because I'm lifting this guy here, I'm using one s variable. So I'm multiplying everything here by s to the power of minus 1, and then I get minus du. And this is like one parameter deformation of this polytope in this degree. So okay, maybe I hope it was clear, but the main thing that I want to state now is, now imagine that that you are able to mutate this thing to a point, which in this case we were able to do. In fact, okay, using this, I mean, if we mutate with 1, 0, we just get this smooth polytope. And so this is smooth polytope. So it means if I write an equations, and then mutate those equations, we will see that by Jacobi criterion we will get smoothing of this guy. Yes.
So you get the smoothing in 2 steps. Then.
Yeah, like in the point is that this works when you construct this FK, you can mutate everything. So you can mutate Hilbert, you can mutate the Hilbert basis, you can mutate the polytopes, and then when you actually achieve a smooth guy, you just go backwards. So for example,
in the middle case, you will have isolated this.
Exactly. Yeah. If you don't, if you don't use parameters, you get isolated. But this t here this is a smoothing of an triangle. This is this one parameter smoothing of an triangle, and it's smooth. Yeah. So if I mutate this guy once again, and so to get if I mutate with our t, I get this one in this case. Yeah. So this is smooth, of course, because this is smooth polytope, and then you just apply this construction. So you mutate back, you mutate down, and how many these t and s are you using? You will see that in fact by Jacobi criterion you get the smoothing of the original polytope. And then there are some more deformation theory needed to the step 2 to actually prove that this is a smoothing component. And so I will just say the theorem, and
what you're saying is that the local moduli space is stratified, and you get the stratum outside the special point under the table.
Yes. So the theorem is that conjecture holds at least for. So constructing this, I need to make some assumptions. But for example, for all polytopes that have two perpendicular, the problematic edges are only the ones that have lattice length more than 1, and I can have 2 perpendicular ones and third one satisfying some conditions so far. But I expect that the procedure is so natural that I expect this actually to hold. And in the same, I mean, this actually can, I mean, the same technique can be then used to prove the whole conjecture. So at least for P being the facet of a reflexive three-dimensional polytope. I was interested in these facets because the three-dimensional polytopes are in one-to-one with Fano toric threefold singular, and so if you understand how facets are deforming, then at least you should be able with this one to get the usual, I mean, all the possible smoothings of singular Fano threefold. So that's, and so this is the theorem. And then, okay, let me just, so doing this computation, it also pops out the following natural conjecture that we track the singular components, like all the components. So there is one-to-one by deformation components of x, and here x affine, Gorenstein, threefold, and something called maximally mutable Laurent polynomials. So this is slightly more general. So maximally mutable means, let me just give an example. And the first, I think the easiest example when this appears is when you take this guy, 4, 5 triangle, so 3, 4, 5. So if you look at this case, and okay, let us first try to without numbers. So of course numbers are 1, 4, 6, 4, 1, and here 5, and so on. So then, right. So these are the binomial coefficients, and okay. So if we try to first look at the zero mutable polynomials, we get it. So the first zero mutable polynomial will be if we look at the mutation 4, 3, 2, 1. So it means these are completely determined by this because it's 4, 3. So this to be divisible by 1 plus y on 3, then these are completely determined by this 5. So this will be 1, 3, 3, 1 multiplied by 5. And then also this guy and this guy. So this is the first zero mutable. And then the second zero mutable is if we take 4, 3, 2, 1, 0. So it means I will just And again, I'm not writing the coefficients, but just like when I put this in red, it means that those three guys are determined by this 4 by doing 4, 3, 2, 1 mutation. And now in the other picture, so I have this. There is another zero mutable, which is coming. So if I take 5, 3, 1, and 4, 2. So 5, 3 means that these are determined, and then because I'm taking 4, 2, it means that these are determined, and then when these are determined, also with 5, 3, 1, this guy is determined. So this is another. So we have 3 zero mutables, and we see that they are all zero mutables. And then finally, what is maximally mutable?
So we have to negotiate about the time now.
I'm already, yeah, sure. Okay, I'm just like writing the.
So, but let's do a small negotiation because I was thinking precisely about this. So, we are supposed not to have a break now and to have later half an hour break. What if we have 2 15 minutes break?
Yeah, I would suggest to have a break, but still.
So let him finish and then we'll reduce the break proportionally to the time.
Okay.
It takes
I'm just, yeah, so sorry, I'll just write one more thing to say. So these are three zero mutables. So what is maximally immutable? Here I'm taking so here I'm taking 3, 2, 1, and then this guy with sorry. So like this, and so this and so maximal immutable is that I'm taking Laurent polynomial that is 3, 2, 1, and then 4, 2, 0 mutable, and then we have that this is not completely determined, which means this is not zero mutable, but in fact we can say that this is maximally immutable in a sense that if we have this mutation, we cannot extend this mutation to be even more mutable. So, for example, we cannot extend it to be 5, 3, 1 because these are already determined. So, in this sense, this is maximally immutable. And the idea is that you can mutate this guy not to a smooth one, but to something that you have that you see that it will be a singular that the deformation exists, and by Jacobi criterion you see that it will not be smooth. So. And then again, like the theorem that I have in this case is also that for P of this type, so like nice P with perpendicular edges, and third one that is of arbitrary lattice length, I can manage to show that in fact you have all the deformation components are in one-to-one with maximal immutable, and the smoothing one corresponds to zero mutable. Yeah, so sorry for all the time.